Okay, so quiz two. Quiz two is all about number systems, and specifically it's about three systems. The binary system, which is base 2, the decimal system, which is base 10, that's the one that we're familiar with, and then there's also the hexadecimal system. Well, the binary system and the hexadecimal system are important in computing. Binary numbers, that's how a computer works internally. A computer really knows nothing. The only thing that exists in computer memory is a series of zeros and ones. We put those together to make a byte with eight bits. We put them together to make a byte, and each byte represents a character, and we put the characters together to make words and language. But to the computers, it's just all zeros and ones. So if you really want to understand what's going on inside a computer, you need to know binary. Now, hexadecimal is another one that's important. And it's important because actually it gives us an economy for expressing very large numbers with few characters. That's why we use hexadecimal in a nutshell. Well, let's just talk about binary here for a minute. So what I want you to see from this first part of the screen that's showing is the similarity between the way binary, decimal, and hexadecimal numbers work. In binary, base 2, there is no 2. You only get to work with 0 and 1. Notice you never get up to 2. You get 0, 1, no single digit for 2. Actually, to express the number 2 in binary, it takes 1 0. It looks like 10, but it's actually 1 0. Base 10 numbers that we're familiar with uses digits for 0 to 9. There is no single character to express the value of 10, unless you're using Roman numerals. It takes 2. It requires a 1 and a 0. So notice that pattern. Base 10, 0 to 9. Base 2, 0 to 1. Well, in base 16, we need to adhere to that same pattern. We need to have a single symbol, a single character, for all the values from 0 up to 1 less than 16, all the way up from 0 to 15. We have to have that in the hexadecimal system. Well, we use the digits from 0 to 9 as with base 10 for those values. But what are we going to do about the values for 10, 11, 12, 13, 14, and 15? We have to represent those with a single character, a single symbol. So what was decided upon, and the very wise decision, was to use the letters of the alphabet, since we're all familiar with those. So A is 10. Here's the kicker down here. A is 10, B is 11, C is 12, D is 13, E is 14, and F is 15. Now, if you were counting in hexadecimal and comparing that to how you count in decimal, if you look at this little table here, all of this, of course, is your base 10 at the top, counting up to 34. And here's how that would work if you were counting in hex. It would go 1, 2, 3, 4, 5, 6, 7, 8, 9, just like it does in base 10. But then at the value of 10, you represent it with an A, according to what we decided upon up here. 11 is B, 12 is C, 13 is D, 14 is E, 15 is F. And then we get to 16 in base 10. Well, we write that as 1, 0 in hexadecimal. 17 is 1, 1. 18 is 1, 2, and so on, all the way through. And then when you get 1, 9, that's 25 in base 10. Well, next highest number after that is 1A in hexadecimal. 1A. Now here's how you have to look at that. You look at that to understand what that is in our base 10 system. Just remember that the first digit of a 2-digit hex number is multiplied by 16, not 10, because it's a base 16 system. We know that in base 10, the number, say 45, we know that means 4 times 10 plus 5, right? Well, 1A in hex means 16 times 1 plus A. And of course, 16 times 1 is 16. A is 10. So 1A is the same thing as 26 in base 10. As long as you understand that, just multiply that first digit by 16. And you can understand how to convert from hex to base 10. Now, when it gets up to 1F, the next highest number after that has to be 20. Now, why is that 32? because that's 2 times 16 plus 0. And so on. And it keeps going like that all the way up to, actually up to FF. All the way up to FF, because we're only going to go up to 255 for this course. Now, what we want you to be able to do, and what the quiz is about, quiz 2, is you're going to have to do some conversions. And one of the conversions you're going to have to do is converting from base 16 to our familiar base 10. And we're only going to use 2-digit hex numbers, so you'll never get more than a 2-digit hex number that you have to convert. Now take a look at this first example here. 4D in hex, we want to convert that to base 10. So we just multiply that, as we mentioned a moment ago, multiply that first digit by 16, and then add the second digit onto it. So 4 times 16, that's 64. D is 13. 64 plus 13, 77 in base 10. That's all there is to it. That's all you got to do to convert a hex number into base 10. 16 times the first digit, add on the second digit. Here's another one. CA to base 10. Multiply the first digit by 16 and then add on the second digit. Well, first in this one case, we have to first understand that C means 12, according to our rules up here, right? The way it works. C is 12. So it has to be 12 times 16, which is 192. A is 10. We add that on. We come up with 202. So CA in hex is 202 in base 10. Any question about that? Got one more here. One more example. FF. Both hex digits are F. So we multiply the first by 16, then add on the second one as before. But F is 15. 15 times 16 is 240. Add 15 onto that and we come up with 255. FF is 255. Anybody that's already got into computer networking will understand that one, because that's a common address used in networking for broadcasting purposes. FF is the biggest number that you can get with an 8-bit byte, and it's 255 in base 10. Any question about that? It's kind of weird. If this is the first time you've seen this, it's strange, but it's really just as simple as I've tried to explain it. Just remember that when you're counting, as soon as you get to 10, that's A, 11 is B, etc., all the way up to 15 being F. And when you want to convert, just multiply that first digit by 16 and then add the second digit on. Okay, not hearing any questions, so we're going to carry on. Now, we also want you to go the other way. We want you to be able to convert from base 10 to base 16. Once again, we'll never give you a number above 255 here to convert. The procedure here is, here's the first example, 77 in base 10. We want to convert it to hexadecimal. Well, the first thing you want to do is divide it by 16. To get that'll give you the first hex digit. Now, it most likely won't divide evenly, but you're just interested in the whole number part of what you get from the division. And that'll give you the first digit. The remainder is the second hex digit. So in the case of 77, 77 divided by 16 gives you a value of 4. And as you know, 4 times 16 is 64. If you subtract that from 77, the remainder is 13. So 77 divided by 16 is 4 with remainder 13. But we don't want to use 13. We have to convert that in hex to D. 13 is D in hex. So the final answer here is 4D. 77 in base 10 then is 4D in hex. So it's just the reverse of the way we did the first conversion. Let's try another one. Here's 203 in base 10. We want to convert that to hexadecimal. So we divide it by 16. That'll give us the first hex digit. Most likely it won't go evenly. That's okay. In this case, 203 divided by 16 gives you a 12. Now, when you do the test, you can do that. You can just, scribble that out on a piece of paper. Do a long division to come up with the answer of 12. And 16 times 12 actually gives you 192, which would mean that the remainder is 11. So 203 divided by 16 gives you 12 with remainder 11. Well, both 12 and 11, we have to convert those into their appropriate hex digits. C is 12, 11 is B. So the correct answer here is CB. CB in hex is 203 in base 10. Okay with that?
I'm going to have to brush up on how to do long division again.
Yeah, that's not a bad idea. I mean, you could do it short way as well if you wanted. Or you could just sort of do it with trial and error. You could experiment with 11 times 16, and you would find that that works out to 176, which is not close enough. So then you try 12. You could eventually get there. Now, we also want you to be able to convert from hex to binary, and I've got a mistake right here that I've got to fix up. This should be base 2. We want to convert it to binary, but that's, of course, base 2, not base 10. Okay, so this is another type of conversion that we want you to do, is from hex to binary. And as it turns out, this is actually quite easy once you get the concept. Here's what we want to do. Here's the principle. Each of the 2 hex digits can be replaced by a 4-bit binary number. A 4-bit binary number, we call that a nibble. Spelled with the Y, because a byte is spelled B-Y-T-E. You don't often see that word, but some books you'll see that. Okay, so here's the principle. Each hex digit in the hex number that we want to convert to binary can be replaced by an equivalent 4-bit binary number. Now, when we want to do that, we only need to refer to the right end of the powers of 2 for binary. In other words, we only need to look at what you can see shown up in yellow here on the screen. These are all powers of 2, right? These are powers of 2. 2 to the third power is 8, 2 squared is 4, 2 to the first power is 2, 2 to the 0 is 1. So all we need to do is look at these and replace each hex digit with the appropriate bit pattern. Well, it's a good idea to look at the 4. Here's the 4. That's the first part of the 4D, right? Remember, we're converting 4D. So 4, we should be able to replace that with 4 bits. And in order to do that, we would turn only this bit on, right? This bit here would be on. All the others would be off to total up to 4. So there's the bit pattern for 4 in binary. In order to get the 110, the D is 13. D is 13. Okay, D is 13. So how can you get 13 with these values, 8, 4, 2, and 1? There's only one way, and that's 8, 4, and 1. So this bit here would be off. The others will be on. And that's all there is to it. Each hex digit you can replace with a 4-bit nibble. Now, commonly when you write an 8-bit byte, it's not unusual to put a colon in between the two, just to sort of separate them into the two nibbles. And by the way, it's also not incorrect to drop a leading 0. So you could drop this 0 here and just express it that way. That's still 4. So you could drop any leading 0. So this is also correct. Just like if I was looking at a classroom full of students, I wouldn't say there's 24 students in the classroom. It'd just be 24. I wouldn't need that leading 0. Anybody have a question about that? I hear somebody chatting. Anybody have a question? Any question? No? Okay. You folks hear me okay?
Yeah.
Yes.
Okay, okay.
Yes.
Give us a little feedback now and then so that I know there's somebody at the other end. Thank you. Okay, so the key is right here. Each hex digit can be replaced with a 4-bit binary number. So let's do another one. E8. I'm going to convert E8 to base 2. Once again, I got to fix that mistake. E8 to base 2 binary. Well, E is 14. See, how can you get 14 with these bits? You'd have to turn on the leftmost 3, wouldn't you? This 8 plus 4 plus 2 would make 14. This bit would be off. So it's 1, 1, 1, 0. How can you get 8? The second of the 2 hex digits. The only way you can get 8 is by turning this bit on. And so the correct answer here is what you see down below. And in this case, there's no leading 0, so we can't turn anything off. So there's the correct answer. So that's hex to binary. Now, you also have to convert from binary to hex. And it's just a reverse process. It's actually just about as easy. All you have to do to convert from binary to hexadecimal is break the binary number into 4-bit nibbles, starting from the right end. So you start from the right end. So starting from here, there's 4 bits. So that's where you have to make the break of the 2 nibbles. So it turns out that I've added leading zeros here. As you can see, this obviously didn't have any leading zeros on it. Sometimes you won't get all 8 bits of a number. It's still a binary number. I mean, you could have much less than that. Like this is the number 7 in binary. It's just 3 ones. That's 7. 4 plus 2 plus 1. You don't always have to show all 8 bits. So break it up into groups of 4 from the right end. So 1, 1, 1, 0 is what you want on the first rightmost nibble, and the second nibble at the front is just 1, 0 or 0, 0, 1, 0 if you like. Well, what does this work out to? If you look at the yellow part over on the right hand side of the screen here, obviously only this bit is on, so that's 2. To get 14, you would have to turn on, 14 is 1, 1, 1, 0, right? That's 14. And how can you get 14? Well, 14 is, if we add these up, it's 8 plus 4 plus 2, 14. And 14 in hex is capital E. Now, sometimes you'll see this hex numbers in lowercase, by the way, as well. But that's basically how you do the conversion. It's like the backwards process of what we did up here.
The little chart that has the yellow on it, how do you get those numbers again?
Well, they're powers of the base 2. Let's see if I can show you another document here.
So it's like 2 to the 5th power.
Yeah, these are all powers of 2. So
2 to the 0, 2 to the 1, 2 to the 2, 2 to
that's right. 2 to the 4th power is 16. 2 to the 5th power is 32. 2 to the 6th power is 64. And 2 to the 7th power is 128.
Okay, I had it backwards. I thought it was squared, and I was like, that's not right. I don't know what's happening.
Yeah, these are all powers of the base 2.
Okay, got it.
That's because it's the binary system, you see? In the binary system, the base is 2. Yeah, it's not a bad idea for you to write this out or have it handy when you're going to do the test. If you're doing the test live in class, if you're one of my face-to-face students, you can bring in a piece of paper and do some scribbling, and you could write this out first when you first sit down, and then you'd be ready.
Okay.
Now, I wanted to show you why this is important, and one of the places where it's important is right here. I've got another window off screen here that I'll bring on screen in a minute. Here's my command prompt on my computer. Now, I've got a blue background. Usually it's a black background. I've changed the color. You can do that too if you wanted to with the properties here. Or pardon me, I guess it's, yeah, it is properties. You can change colors and stuff like that in this so-called DOS window or command prompt window. But what I wanted to show you here was, does anybody know how to get the IP address of their computer at this point? There's a command I can enter right now. It will give me all kinds of information about my connect.
IP config.
Excellent, excellent. IP config, very good. So if I type that in, IP config, you'll notice I get a screen load of stuff about my computer. And I wanted to show you a couple of things. First of all, my Ethernet adapter is in hex. Actually, that's my IP version 6 address. Notice F and E in a few places. There's a D and an E. Now they're lowercase. It's not unusual for hex numbers to be in lowercase instead of uppercase. So one of the reasons that we need to understand hex is to understand that IP version 6 addresses are going to show up in hex. Okay, once more, here's some more hex. Where you see the F, this is a good one down here. Look, we've got C and B, but you're never going to see anything greater than an F there, because that's all you get to work with in hexes from A to F. Okay, so just wanted you to see that. That's one of the reasons why we need to know hex. Well, that's about it. That's about all I had to show you, except back on our course page, I'm going to go into, for a second, I'm going to go into Module 8. And if we go into Module 8 and click on Learn Number Systems, there's a number of resources in here for you. Incidentally, that document that we just went through, this is it right here. That entire Word document, this is it. But there's some other stuff here that we can look at too. I think actually these two are the same. But let's take a look at this one here. This might help you. Maybe we should have done this one first, because I believe this one's about binary. Yeah, this is a little video I made up. We'll show you how to convert from binary base 2 to decimal base 10. Here you can see that it's the same values that we had in our little diagram that was next to the examples that we did. So these are powers of 2, and we've got 8-bit bytes down here, and we can turn on values. I'll let this run for just a bit, if you don't mind. You may have heard about a byte. A byte is 8 bits of data, numbered from 7 down to 0, from left to right. From 7 down to 0. Now, if you take those numbers and use them as exponents of the base 2, you'll come up with these numbers: 128, 54, etc., all the way down to 1. When you look at an 8-bit byte, remember that an 8-bit byte consists of 8 bits, and bits can only be 0 or 1. All you have to do to convert from binary to base 10 is add up these numbers for the bits that are on. So you notice here, only 1 bit is on. That's a 1. So this is the equivalent of 1. To get 2 in base 10 in binary, you turn this bit off. That's the only one that has to be on because it's with 2. To get 3, you have to turn these 2 bits on. 2 plus 1 equals 3. Here's 4. only one bit has to be on. That one is worth 4. To give you 4 in base 10, and so on. That's the way it works. Here's 8. Skip a few. To get 8, only this one bit has to be on. It has a value of 8, and so it looks sort of like 1,000 if you look at it. Okay, it looks like 1,000, but in binary, that's just 8. Okay, let's try a random one. We can try just turning on a few here. All right, that turned out to be 170. Now, why is that 170? Let's check. Here's 128 plus 32. That's 160. And here's 8 more, 168. And here's 2 more, that's 170. So you add up the values up here for the bits that are on, and you can convert easily from binary to base 10. So that's how you convert from binary to base 10. Just add up the values of the bits that are on. Now, why do we want to do this? Computers only understand ones and zeros. We humans want to work with letters of the alphabet, digits, punctuation, characters, etc. So we need some kind of a coding scheme that relates zeros and ones to what we want, letters of the alphabet. And that's where the Ascii coding system comes in. The Ascii coding system was developed in the early 1960s, and it's the Rosetta Stone that relates what a computer can understand. A computer can understand anything. Zeros and ones, what we understand, characters. Here's how it works. In Ascii, each possible 8-bit byte is assigned to an alphabet letter, digit, punctuation, character, or something else that you might find on your keyboard. And we can look them up. Here's one that I found with a quick Google search. Here's the binary, and that actually works out to 65. 64 plus 1. And here it is 65. Well, that happens to be capital A in the Ascii code scheme. Each bit pattern of 8 bytes that is represented by a character in Ascii. Let's go back here for a second, and we'll back to our spreadsheet. And if I turn this on, and this bit on, I do get 65, 64 plus 1. And as we saw a moment ago, that's capital A. Well, to get capital B, that's actually this bit on, and this bit on, 66. And similarly, that's 1 to get capital C, that's 1 plus 2 plus 64, 67. You see why that's 67, 64 plus 2 plus 1, referring to these numbers up here. I'm adding up the powers of 2 for the bits that are on. Okay? Now, Ascii was developed, as I said, in the early 1960s, and the key for you with converting from binary to base 10 is just remember that you're setting the ones and zeros every time you press a key. I'm going to insert one more right here. I'm going to insert another row, and if I, in that row, if I enter a 1 here, zeros for most of the remaining bytes, except 1 here and 1 here, that works out to 97. Well, that happens to be lowercase a, and I'd like you to examine these two rows for a minute. The only difference between uppercase A and lowercase a is that bit 5 is on for lowercase and on for uppercase. So when you hold down the shift key and type letter A on your keyboard, you are basically turning off bit number 5. Okay, but here's a little bit about the Rosetta Stone. It was found in the desert, and prior to... Yeah, I'll let you read that. But that's basically it for binary, and that's why we need to know binary. The other thing that we expect you to do is change from base 10 to binary, and also from binary to base 10. And you can do it if you just keep these numbers here in mind. And you might think there's more than one way to get a particular value, but there's not. If you turn all 8 bits on, you get the sum of all these numbers here, and that's 255. And you might think, well, there's probably 2 ways to get the number 239. Nope, there's only one way. There's only one bit pattern of 8, one pattern of 8 bits that gives you 239, or any other number from 1 to 255. Okay, so I want to make sure you saw that, but let's see what else is back here on our course page. I think we have a few more things that you could look at. There is a YouTube here about number systems. I want to see what that looks like.
Hey guys, does this day sound familiar? During a confusing lecture, you ask for help. You need to know how to convert from binary to decimal, vice versa. You also need to know how to work with hexadecimal and convert from binary to hexadecimal and vice versa into decimal and all these different.
So this teacher somewhere else in America, he's got this video, and I encourage you to take a look at it. It might help you to understand some of the stuff that we did today. You might do it in a slightly different way, which is also okay. There's different ways of doing the conversions that make sense. One thing that you want to understand is when you do the quiz 2, to get full points, you do have to show a solution. You have to show a method, kind of like your math teacher required you to do when you submitted the answer to a math problem. You couldn't just put the answer in, right? You had to show your steps and how you got it. Well, we would like you to do the same thing for the number systems test. Don't just put the answer alone. That'll only give you half points. So you want to use some kind of a method, something like what we did here. Like I would call this an acceptable method, for example, for this problem. It's a series of steps like that. Okay, so that's kind of how it works. Now you could practice this as much as you want by using the Windows calculator. Just fire that up and show you how that could work for you. If you fire up the Windows calculator, and I can move it around here a little bit.
We can, when we take the class, the test in class, we can use the Windows calculator, right?
No, you can't. No, I'm sorry.
You can't use a calculator at all?
No, I'm sorry, you can't. But I wanted you to see what you can do here. If you change to the non-standard calculator, if you choose instead the programmer version of the calculator, look, hex, decimal, binary. They even have octal, which is base 8. Now we're not concerned with that. But let's say if I choose hex here, notice when I hit hex, the letters A to F become available to me. So I can type in a number like, say, for example, F7. Well, there's what it is in base 10, and there's what it is in binary. So you could practice by using this. You could just write down any old number at all in either hex, binary, or decimal. Switch it back to decimal, and I could type in a number like 46. Well, you can see right away there's what it is in hex, there's what it is in binary. So you could sort of check your work as you try to do conversions with this, but you're not allowed to use it on the test. It's very important to be able to, actually, if you become a professional network engineer or network administrator, this has to be second nature to you. You just look at the number and you know exactly what it is. And that will happen with practice. Okay, so I just wanted to make sure you're aware of that. There's lots of other stuff online. You can get apps for your phone, whether it's an Android phone or an Apple phone, an iPhone. You could get an app for conversion as well on your phone. You can use that to practice. And there's a good instructional apps as well for your phones. So that's about it for the for the conversion. Let's see here. I wanted to show you one more thing, I guess. If I go right into the course content again and look at the quiz, it's not available. It won't show up until a certain date. And the quiz will show up on December 2nd. Actually, it starts on December 1st, I should say, and it's due by 11:59 p.m. Now that's for online students. If you are one of my day students, we'll be doing it in class a week from tomorrow. Okay, but here's what the test is all about. You got 6 questions to do, 6 conversions. There they are. For full points, you got to show a solution, not just an answer. So you want to practice a little bit.